So what we're trying to get a good understanding of is Schrödinger's model of the atom. Now Schrödinger's model of the atom basically comprises of electrons which are trapped within the potential created by the nucleus. Now in order to build up this understanding, let's base it on something that you've seen before, waves on strings. So you've seen for a wave which is travelling along a piece of string, if there's no constraints on the piece of string, so infinitely long piece of string, then that travelling wave can basically have any reasonable frequency. Now, the equivalent thing to frequency for our wave is the energy for the electron, which is making up our matter wave. So it's just easier for matter waves to consider energies rather than frequencies. So for an electron, which is completely free, so not bound to the nucleus or anything, just completely free to move anywhere, it can have any reasonable energy, just as our travelling wave could have any reasonable frequency. Now if we clamped our string, we force it to have nodes at the two places that we clamp it, and we saw that for waves this set up standing waves, and when we had standing waves on that clamped string, there was only certain frequencies that those standing waves were allowed to have. Well, an exactly equivalent thing happens with the energies for an electron. If we trap the electron by applying a force which creates a potential, then we end up with only being allowed certain energies. So what we're going to do is we're going to start with the absolute simplest trap, which is an infinitely deep potential well, and we'll look at what energies this allows an electron to have.
Okay, so let's start by considering what a potential well, infinite potential well actually is. It's a well with an infinite potential outside. So if we let this end of the well be at x equals 0 and this end be at x equals L, then we've got a potential equal to, say, minus infinity out here and minus infinity here. And the potential energy for an electron with a negative charge is related to the potential through U is equal to minus EV. And inside here we've got 0 potential. So here the potential energy is infinite, here the potential energy is 0, and here the potential energy is infinite. So this is basically forcing our electron to be in this region here. So mathematically we can write this down as when x is less than 0 or equal to 0, then the potential is infinite. For x is less than 0 is less than L, so in this region here, then the potential is 0. And for x is greater than L or equal to L, then the potential is infinite again. Now, just as for standing waves on a string, where we could only have an integer number of half wavelengths within our piece of string, exactly the same thing happens on this well. So the electrons cannot be outside in this infinite potential region, they have to be inside the well. And so we've got exactly the same relationship. Our length here, the length of our well, is equal to an integer number of half wavelengths. So what we're trying to get is a relationship between the energy of the electron, the allowed energies, and the length of our well and whatever other appropriate quantities. Okay, so one thing we do know is we know inside it's got 0 potential. So the total energy is equal to the kinetic energy plus the potential energy. Inside the potential 0, so this is equal to K inside. We know it's an electron, so we know that K is equal to a half mv squared, and we can write this as 1 on 2m times mv squared, which is equal to 1 over 2mp squared. So this tells us that P, just rearranging it because we've got an E here, we know that P is equal to the square root of 2me. And how this is useful is that we know from de Broglie's relationship that P is equal to h over lambda. So we know that lambda is equal to h over p. So we've got lambda, which we can get from up here, just rearranging our equation here. We've got lambda is equal to 2L on n. So we've got 2L on n is equal to h over p, which is the square root of 2me. And now we're starting to get this expression for E in terms of L and the other properties of the well that we know about. So we can rearrange this. So we've got 2me square root is equal to h times n over 2L. So 2me is equal to h squared n squared over 4L squared. And so E is equal to h squared. 2m comes down the bottom here, so we end up with 8ml squared times n squared. And so that gives us the allowed energies for these trapped electrons. So n can be an integer, so 1, 2, 3, etc. So we would have, for example, E1, the lowest energy state with the half a wavelength like this here would be h squared over 8ml squared. But we can substitute in these other integers as well.